Hello all, optimization, lesson 3.7. So why optimization? Remember that the title of the chapter is applications of the derivative. So what are some real life applications or examples of using the derivative? This would be more so than any other. Using optimization, you're looking to maximize or minimize some given quantity. So maximum volume, max or min, distance or length, area, maximum profit, minimum cost. So the problems that we solve, you'll be asked to find a maximum value or a minimum value. All right, we'll start with a simple example. And you did look at these last year, but they were only quadratics because you could find the x-coordinate of the vertex, and then that would be your max or min value. Find two numbers whose sum is 20 and whose product is as large as possible. Okay, what do we know? Two numbers whose sum is 20, and we're looking to maximize their product. So we're looking to find what the largest value of x times y would be. And I'm sure you already know what the answer is, but let's do it very quickly. You'll see on the guidelines that I give next, this is what the book refers to as your secondary equation. It gives you information about the variables. This is what the book refers to as your primary equation. That's the equation you're looking to maximize or minimize. Take the secondary equation, solve it for one of the variables, and into your primary equation, make this substitution. Now we have one equation in terms of one unknown. Distributing the x. Okay. Applications of the derivative. When in doubt, take the derivative. The derivative of this function, 20 minus 3x squared. Critical numbers. Where does the derivative equal 0? Where does the derivative not exist? Oh, I knew something was looking not right. This is just x. 20 minus x. So when I distribute that, well, the possible domain could be any number, positive or negative. Determining where the derivative equals 0, we get x is equal to 10. And again, I'll put the guidelines up. You have to verify that it's a max or min. And this is where the second derivative test becomes useful. So you just completed a quiz on determining critical numbers, putting them on a number line, doing a sign analysis. The derivative switches negative to positive relative min. Derivative switches positive to negative and relative max. Well, our second derivative test, and if you haven't watched that video, please do so. The second derivative of the function is negative 2. Okay, here's the first derivative, so I derived that function. The second derivative test says, take the critical numbers where the derivative is equal to 0. In this case, x is equal to 10 is a critical number that satisfies that. Into the second derivative, place that critical number. Look at the sign of the second derivative. The second derivative is always negative. A negative second derivative means our function is concave down. So at the point where the derivative equals 0, which would be a horizontal tangent line, on a concave down function, x equals 2 would maximize the function. Since x equals 10 is a max, go back, make sure that you answer the question, find two numbers whose sum is as large as possible. So if x is equal to 10, go back into the secondary equation, replace the information that we have, and y. And again, last year you looked at this, but a square would always maximize an area. So x equals 10, y equals 10 are the two numbers with a sum of 20 whose product is as large as possible. So take a minute and please write the guidelines down in your notes. I will refer to these. When you get to number 4, all right, we do discuss domain restrictions. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches What dimensions will produce a box with maximum volume? Primary equation. We're looking to maximize the volume. This example's from the text, so they do give you a figure. You're not always given a figure. That's why the first direction is to draw it and label it if possible. What's the maximum of this box? Area of the base. We're told it's a square base times the height. Now notice your equation here that we want to take the derivative of is in terms of two variables. That's why we need this secondary equation. So look in the problem for another piece of information. So we're told that we have the box has a surface area of 128 square inches. Surface area, that's the area of the base, plus the area of the sides. Look at the area of the sides, x times h, and there's 4 of them. And we're told that the surface area is 108. Now look at your options to solve for. I would suggest solving for h, because if you wanted to solve for x, you would have to, it's just, don't do it, all right? So get h by itself. Subtract x squared from both sides, and then divide both sides by 4x. From the secondary equation, once you've solved for the one variable, make that replacement into the primary equation, the equation that you're looking to maximize or minimize. In this case, maximize. Those x's will cancel. Again, applications of derivative. So we've already developed all of our derivative rules. Algebraically, do anything that you can before you dive into a derivative. Okay, so I simplified the x's, distributed the x there, so I don't need the product rule in order to find the derivative. And now I am going to simplify this even further. So we have 27x minus x cubed over 4. Okay, so volume equals 27x minus x cubed over 4. Now let's take the derivative. 27 minus 3/4 x squared. Find the critical numbers, and this is where the domain restrictions come in. So we were told that the surface area was equal to 108. All right, so to find what the endpoint would be, so the area can't be bigger than 108. So the side length has to be less than 108, which will be it'll be less than 11. Okay, it'll be somewhere between 10 and 11. We know we're talking dimensions of a box, so they can't be negative dimensions, and we'll represent that. Now let's look for where does the derivative equal 0. Multiplying by 4/3. 9 times 4, 36 equals x squared. Taking the square root, we get 2 critical numbers. But again, on the domain, so the feasible region is the open interval between 0 and the square root of 108. So we would eliminate -6 from our possible values. So verify x equals 6 is a maximum. This again is where the second derivative test is helpful. So the second derivative of the function, -6/4 times x. All right, derivative of 27 is 0, then just using our power rule. So the second derivative at 6 is going to be a negative value. Therefore, x equals 6 is a maximum. So what dimensions will produce a box? So we found x, and now we need to solve for the height of the box. So going back to that secondary equation, so that gives us 72. So what dimensions will maximize the volume? X equals, okay, inches. So we got X equals 6 inches and Y equal, or height, excuse me. All right, you're going to hate this one. What point on the semicircle comes closest to the point 1 comma square root of 3? So we're attempting to find a minimum distance. What's the distance between 2 points on the coordinate plane? Difference in the x's squared plus difference in the y's squared. All right, now what's nice, the length is the smallest when what's underneath the radical is the smallest. So we don't have to worry about the square root, which will save us a lot of time on the derivative. Okay, so we're looking x minus 1 quantity squared. This is the primary equation. That's what we're looking to minimize. So this is our secondary equation. So we're going to use that to substitute in for y. All right, so we need the function we're attempting to maximize or minimize, we need it in terms of one variable. Well, what's y equal to? It's equal to the square root of 16 minus x squared minus the y coordinate, quantity squared. Algebraically, square, double, square. Same goes for this. It's not as nice looking, but square the first term, gets rid of the square root, minus 2 times the product, and then square the last. These cancel. 17 and 3 gives me 20. Now I'm going to distribute the 3 in. 48 minus 3x squared. Okay, we're told this is a semicircle, so let's talk about the domain of this function real quickly. We know that what's underneath here can't be a negative value. A semicircle, if we were to square it and get x squared and y squared on both sides, the domain of this function is all real numbers between -4 and 4. So that'll become important with the derivative. -2, derivative of 20 is 0. Times the derivative of the inside. So d prime is -2. -1 times -6 plus 6x. Okay. So we'll finish this problem. For your homework for class, our next class meeting, find the critical values. So we got the derivative. Where does the derivative equal 0? Where does the derivative not exist? So come to class prepared with those values.